Welcome everybody at fourth lecture of astrochemistry lecture course. This lecture will be given by Professor Alexander Tielens from Leiden University and University of Maryland, and he will speak about the cosmic life cycle of matter and environmental conditions in space. So, Alexander, please, the floor is yours.
Thank you. So I've divided this lecture into two parts. The first part will give you an overview of the life cycle of matter in the galaxy. And in the second part, I'll zoom into molecular clouds and give an overview of molecular clouds and how they fit into this life cycle. There are some resources that you can access, that you can, if you want some further and deeper understanding of this. One is my textbook in 2005 on the physics and chemistry of the interstellar medium, which is particularly relevant for this discussion on the life cycle of the interstellar medium. And then I wrote a second textbook, Molecular Astrophysics, which is more relevant when you talk about when you consider molecular clouds. I'll make the slides available afterwards as PDFs. And if you have any questions, you can always email me at this email address. And I tend to react relatively quickly, as quick as I can. Now, in molecular astrophysics, we study it because we can use those molecules to study the universe. Molecules are very good thermometers, barometers, and densometers. So measuring the temperature, the pressure, and the density of the gas. But molecules also play an important role in physical processes that control the structure of the interstellar medium. And then, of course, molecules lock up much of the biogenic elements. And so they control the volatile and organic inventory of newly forming planets. And that's why molecular astrophysics is really at the heart of one of the key questions in astronomy. Is the life elsewhere, and are we alone? And those are questions that humanity has been considering forever. You know, this is one of the defining questions for mankind. But in this lecture, I will focus on the interstellar medium, what makes the interstellar medium tick, and so I'll describe what's the large-scale structure of the interstellar medium. I provide an overview of the physical conditions in the different components of the interstellar medium. I'll touch a little bit about the molecules, but I think most of that will be considered in the other lectures in this series. And I'll touch briefly upon how molecules can be used to study the interstellar medium, particularly in star-forming molecular clouds. So let's start about the ecology of the interstellar medium, and then that's really a story about the massive stars and the interstellar medium. And massive stars are formed in dense molecular clouds, and they're very massive, very energetic. They pump a lot of radiative energy and a lot of mechanical energy into the cloud. And that radiative energy can ionize the gas and create H2 regions. They can photodissociate molecules, creating photodissociation regions. And they can create a photoevaporative flow, so a flow of material from the surfaces of the cloud into the general interstellar medium, thereby destroying the molecular cloud. Then, of course, the mechanical energy that's put in by stellar winds that will expand and that will sweep up the surrounding material, create dense shells. Those dense shells can eventually form new stars. At the end of their lifetime, massive stars explode as a supernova, and all the elements that they have created in their over their lifetime will be ejected into the interstellar medium. And these supernova remnants are very obvious when you look at the galaxy. Most of the mass of stars is actually in low mass stars. So there are many, many, many low mass stars, and they lock up much of the gas in stars that evolve really very slowly. A massive star lives maybe 5 million years. A low mass star lives, a star like the sun will live 10 billion years. But eventually, those low mass stars will evolve into what's called asymptotic giant branch stars at the end of their life, and then they will develop a slow wind which returns much of the material back into the interstellar medium. And at the end, they leave a planetary nebula as the central object evolves into a white dwarf, a hot white dwarf, which can ionize that shell of ejected mass and create these beautiful butterfly-like structures that you may remember for having seen in Hubble images. For the asymptotic giant branch stars, the gas, ejected gas, is enriched in carbon, the element carbon, as well as process elements, and much of it is the mass is returned in form of molecules and dust. If the mass of the white dwarf exceeds the Chandrasekhar mass, about 1.4 solar masses, then you will get a type 1 supernova explosion, which will return all of the mass back into the interstellar medium, and that will also be enriched, and mainly particularly in iron. This is a schematic of what I was just saying. This is a molecular cloud indicated here in brown. Massive stars have formed. Their stellar wind has created this bubble, have ionized it. Eventually, it will evolve as supernova, create a rapidly expanding supernova remnant. If there are many, many supernovas exploding in a small area, then you get a super bubble, and that super bubble will break open and will set up a flow of material out of the plane of the galaxy into the halo, the lower halo, from which it condenses down as clouds and rains down onto the plane and becomes part of the rest of the interstellar medium. As I said, most of the mass star forming returns low mass stars. Those evolve much slower. Very low mass stars don't evolve much over the age of the universe, but a star like the sun will evolve over 10 billion years, create this asymptotic giant branch star, which will then create these planetary nebula and leave behind the white dwarf remnant. And so it's this life cycle, and that's why we call it the life cycle. And there is some ecology going on because you have rain, these clouds rain down on the plane. And it's this cycling that enriches the interstellar medium, is this cycling that drives the evolution of the interstellar medium, it is cycling that drives the observational characteristics of the interstellar medium. And so what I'll do next is take you through a number of examples of the kind of regions I was talking about, so you get some feeling for it, and you also get to enjoy some pretty pictures. So this is the Huygens region in Orion. There are 4 stars here, the trapezium stars, and the most massive of that one is Zeta 1 Ori C. And its radiation has created this ionized gas that you see here in blue, and it's on the surface of a cloud. And so this is the edge of it. This is a dense photodissociation region. All the ionizing photons, hydrogen ionizing photons, have been used up. And all of this is only heated by far ultraviolet photons, whose energy is less than 13.6 eV. And it's the most massive star of a star-forming region. It contains about, I forget, 40 solar masses of gas, this one star. But most of the stars are low mass stars, and there are about 1,800 solar masses of these new low mass stars. So a few thousand stars have been formed in this dense core that's behind it. And so this is an H2 region. In front of this, inside of this H2 region, you will find some of these low mass stars, and they are still surrounded by their disks, their protoplanetary disk, planet forming disk. And some of them you see in silhouette here against the bright background. Some of them are inside the stellar wind region, and so they form this nice cometary kind of structure where the wind sort of blows around it. Here's another example. And so these stars, these low mass stars and the planetary disk, are much affected by the massive star that's ionizing and creating all this havoc in its environment. And the sun was formed in this kind of environment as well, we think. Here's an example. We're still looking at the Orion Nebula, still a somewhat larger scale size. So this is now a few parsecs across. Here's the trapezium stars. Here's that Huygens region that we saw in the previous picture. And now the red glow that we see here is infrared fluorescence from large polycyclic aromatic hydrocarbons. And you can see that this stellar cluster has created this large bubble that you see outlined here on the sky. And the inside of that bubble is filled with hot gas from the stellar wind and with ionized gas where the stars are ionized in the insides of this bubble. There are two other H2 regions here, small ones. This is M43. There's a B0.5 star here. It's a much smaller region. And then up here is NGC 1977, which is ionized by a B1 star. So those are much less powerful. They don't have much of a stellar wind, but they still create bubbles because they ionize the environment and the overpressure drives an expansion. All of this is embedded in a large molecular cloud, and we're now looking at a scale size of some 10 parsecs this way, 4 parsecs this way. And this is ammonia that traces really the densest gas. And this looks like an integral shaped structure, and that's therefore called the integral shaped filament. And in the densest portions of this filament, new stars are formed. Here is the Orion region that we talked about just a few minutes ago. Here's the M42, the Huygens region. Here is NGC 1977, and there are a number of dense cores that are forming this these stars. This is OMC1. OMC2 is here, OMC3 is here, OMC4, and OMC5. So the star formation is really limited to the densest cores. This is then a supernova remnant, this gas A. So this now we're shifting from the formation of the stars to the end of the stars. And this is a rapidly expanding shell. The gas is expanding at about 10,000 kilometers per second. That creates a shock wave, sweeps up the medium, and the shock cools through emission in various lines. And this is the emission that you see in the silicon line, the sulfur line, calcium, high energy X-rays, and iron. And when you put it all together, you get this beautiful image showing that the stellar ejecta, because there's mainly stellar ejecta that you're seeing here. And they're heavily enriched in these elements by about a factor of 10. Now we're zooming out to an even larger region. This is now a few hundred parsecs in size. So here is Orion A. That's that integral shaped filament. The H2 region is down here. You can see that there is a much larger, lower density cloud around it, indicated here in green. Here's Orion B, another molecular cloud with its star formation. There is this red glow that's due to recombination of ionized hydrogen, and that's Barnard's loop. You see a lot of red glow here as well. That's ionized gas that's escaping. And you see this green material, which is molecular clouds. This is Monoceros, and this is Orion A, and this is Orion B. And so we're talking now about a scale of a few 100 parsecs. If we zoom out even further, then here this is a slightly different view, just for you to orient yourself on the sky. So here you see the Orion constellation. You recognize the shoulders, the belt, the sword is hanging down, and the tip of the sword is this Orion Nebula. And here are the knees, and here is the head. And star formation has been going on in this region for about 12 million years. The Orion A region that we were discussing before is very young, maybe 100,000 years old or so. And there are 4 OB associations that can be recognized in this 1A, 1B, 1C, and 1D. And they are spread over this whole area, and 12 million years old. That means that some of the stars, the massive stars in the older association, have already gone supernova. And we can see that if we zoom out to an even larger scale, this is now 400 parsecs on the side. You can recognize again Orion A and Orion B. Here's Barnard's Loop. This is Lambda Ori, so that's the head of the Orion constellation. Here above here is the galactic plane. And you can see here the edges of it, of a large bubble, a super bubble that the supernova energy has created. And so all of this is filled by very tenuous, talking about density of 10 to the minus 3 or so particles per cubic centimeter, but a very hot gas, 3 million years or so. And these molecular clouds are embedded in this super bubble, as is the Barnard's Loop. And these filaments are really the edges of this super bubble. Now, if you zoom even out even further and look at where is the sun, then the sun is actually, we're looking down on the plane of the galaxy now. So this is, here is the sun. And you see that we are inside one of those supernova bubbles. This is called the local bubble. Many of the other stars, nearby stars, are embedded in that as well. There's a lot of local fluff, really low density material that's floating around inside this. And these bubbles are created by supernovae, and the supernovas expand and sweep up these dense shells of gas. And that forms a foam-like network filled with tenuous hot gas. And you can see that when you zoom out a little bit more, we're now talking about 500 parsec in radius region. The sun is here. This is that local bubble, but you can see that there are a number of other bubbles. This is called loop 1, loop 3, loop 2, and down here is the Orion Eridanus bubble that I showed a little while ago. And you can see that many of the nearby regions that we well know from star forming studies, like Chameleon here, Ophiuchus, Taurus, they are in these dense shells that have been swept up, and they are presently forming stars. This is on an even larger scale. We're now talking about a kiloparsec in size. And let's look for the sun. The sun is here. This is in German, so it's called Sonne. This is that local bubble, loop 1, loop 3, loop 2. You can see here the Orion Eridanus bubble, but you can see that there are all these structures that are created by expanding supernovas, which are then breaking open and coagulating and forming this foam-like network. Now, if you zoom even further out and look at the whole galaxy, then you see that the galaxy, our own galaxy, has a central bar, and spiral arms are connected to that. And you see 2 main spiral arms here, and then there are these spurs that are breaking off from these arms. And the sun is here now, about 8 kiloparsecs from the galactic center. And we're talking now about a scale size of about 30 kiloparsecs on the side. This is a whole galaxy. So the massive stars play an important role in the ecology. I've already mentioned that, because they create these regions of hot gas that are rapidly expanding, and they can create these super bubbles like the Orion Eridanus super bubble. And they expand, and of course they expand preferentially in regions of lower pressure, so into the halo. And then they may break open and eject their material into the lower halo. And material in the lower halo can then condense down again and fall as clouds onto the galactic plane. And so you have this cycle of material that I mentioned a few times. So this is a side view of the galaxy. This is the galactic plane, which is really very thin. This is a top view, just like I showed before, where you have these different stages. You first form H2 regions, you get your supernova going off, form supercells and superbubbles, which then vent into the halo. So there's a lot of mixing, there's a lot of turbulence going on that creates all the structures that we see when we look at the galaxy. So this is then sort of a summary of the different kind of regions that you encounter in the interstellar medium. And I've given, this is the general name, H2 region, and on this side is a specific example that I showed in the slides before in the pretty pictures. So from H2 regions, the Orion Nebula, photodissociation regions, the Orion Bar, the supernova remnants, young supernova remnants, gas A, then the superbubbles, Orion Eridanus, molecular clouds, Orion A, and the integral shaped filament, and molecular cloud cores like OMC1, in which the star formation was occurring in Orion. This then is a larger table where you have, again, these first two columns are what I just went through, and then you have some columns describing the densities and the temperatures and the processes that regulate the ionization and the energy, because those are important when you want to understand the physics behind it. And you can see that the densities and temperatures range considerably from low temperature of about 8 or 10 degrees all the way up to 10 million degrees, and densities of 10 to the minus 3 all the way up to 10 to the 5th, 10 to the 4th, 10 to the 5th particles per cubic centimeter. And so trying to understand this, we have to understand the processes that play a role in this. And a key aspect in this and understanding this is the cooling of the interstellar medium, cooling of atomic gas. And this is that cooling curve. So this gives the cooling of a gas as a function of temperature. And at low temperatures, you can only excite transitions that have small energy differences. And so you can only excite atomic fine structure lines. And the dominant one is this carbon-2 158 micron line. But if the temperature rises to about 10,000 degrees, then you can excite transitions which are separated by 10, 20,000 degrees. And so you can start to excite these low-lying electronic levels of say, oxygen 1, and that can take over the cooling then. And if you get really high temperatures, then you can even excite the H1 Lyman alpha line. Of course, if you go to even higher temperatures than that, then all the hydrogen is ionized and it cannot cool anymore, but there are still ionization stages of carbon and oxygen that can play a role. Eventually, at very high temperatures, only iron still has bound electrons, and so only iron can still cool. And when you get to really very high temperatures, so 3 times 10⁷ or higher, then everything is ionized, and the only cooling occurs through Bremsstrahlung, through the interaction of an electron passing by a nucleus. Now, the interstellar medium is largely in thermal equilibrium, so it means that heating equals cooling. The heating can be described in a term that's indicated here by gamma, and the cooling is described by lambda. And the cooling, of course, scales with density squared, because you need to have a collision between an electron and an atom to excite it, so it can cool down, radiate will cool down. Heating, on the other hand, can scale with the density. Say if you have cosmic rays that are ionizing, then it only depends on how many atoms this cosmic ray will encounter, and so it scales with the density. So if these two terms balance, then you can take them and divide them by n² kT, and that means that you get on this side the heating term over the pressure, and on this side the cooling term over kT. And this is just atomic properties. The cooling curve is atomic properties. You can calculate this if you know your atomic structure and the properties and the electronic levels of your molecule, of your atom. And you can take this curve and divide it by KT, and that gives you then this side of the equation, and then you know that this side has to equal the heating over the pressure. And so if you divide the cooling curve by KT, then you get this curve. And that has to be equal to the heating term over the pressure. And it's plotted here as a function of temperature again. And then if you have a constant pressure and a constant heating, then that's a straight line on this curve, on this diagram. And so that straight line will intersect this curve in 4 places, these 4 places. 2 of those places are stable, thermally stable. This is a low temperature phase and therefore dense. It's called clouds in astronomy. This is an intercloud region. It's a much higher temperature and it's a much lower density. These 2 phases are unstable. So any gas that's in this phase will quickly be driven either to the cold phase or to the warm phase. And so this is just the property of the atoms, the property of the cooling, that leads to the presence of these 2 phases, clouds and intercloud material, which can exist in thermal equilibrium and in pressure equilibrium with each other. Now you can think about this slightly differently. Let's consider a cloud. And that cloud is in thermal equilibrium, and it's then being cooled by carbon plus because there's low temperature. And when the density in that cloud were to drop, then the cooling will drop. And it will drop faster than the heating, because remember, the cooling scales with collisions, so with the density squared, while the heating only scales with the density. And so what will happen is that if the heating drops, if the cooling drops faster than the heating, then the gas will have to get hotter. The gas will have to get hotter to take advantage of the Boltzmann factor. The Boltzmann factor says that the fraction of the excited atoms that can radiate down and cool scales with the energy separation divided by KT in an exponent. And that will work. That thermostat will work until the temperature of the medium reaches sort of the level separation of the energy separation of the 2 levels involved, which for the carbon plus line is about 100 degrees. Once you're above 100 degrees, this trick doesn't work anymore. So the gas cooling will not increase much because you have reached that you cannot excite the gas more. Instead, what will happen is that you will have to switch on a different cooling mechanism. And the next cooling mechanism, if you look at the cooling curve, is this oxygen 16300 angstrom line. And that's a level separation of about 5,000 degrees. So that means that you need to reach that kind of a temperature. And so that leads to the phases where you have high densities and you're cooling with the carbon plus line, and another phase where you have low densities and you're being cooled by oxygen 1. One phase which is 100 degrees, one phase which is maybe 5 or 8,000 degrees. And that's just the property of the atoms that controls the structure of the interstellar medium. This is then a calculation that takes everything into account. The whole kitchen sink is involved in this. But you can again here recognize it's plotted here, the phase function is plotted here in terms of the pressure versus the density. And so temperature increases along this line and, decreases along this line. And again, you see that for constant pressure, you have these different phases. This is then, this bottom diagram plots then the different cooling and heating mechanisms that play a role at the different densities and pressures. But the basic point is the same, even if you do a large calculation that involves everything. You have this warm and neutral medium, and you have this cold neutral medium, which are in pressure equilibrium, which are in thermal equilibrium. Now we have seen that besides these two clouds, we also have a hot intercloud medium. The hot intercloud results from kinetic energy input, mechanical energy input. So you shock gas, create a very hot phase, cannot cool very efficiently, and it cools by adiabatic expansion. You create these bubbles and these super bubbles. We also have molecular clouds. And molecular clouds exist because they are gravity dominated. And that leads to these large structures in which then eventually stars can form because gravity can take over. This is a numerical simulation that puts this in perspective for you. This is a crosscut of the galactic plane. So this is Y and this is X in the galactic plane. This is the Z direction in the galactic plane. So up above the galactic plane and below the galactic plane. This then is the density, the temperature, the velocity, and the magnetic field. And so when I start this, you can see that you form dense concentrations, and in these dense concentrations, you form stars. You can see some of them forming, and then when they go supernova or they're stellar winds, you can see that they create these cavities filled with hot gas. And most of it expands upwards into the medium, but you can see that sometimes here there's blue material that will flow down, and on this side there's red material that flow up. Red and blue are whether you're up or down. And this goes on and on. This is what drives the life cycle of the Milky Way. You can see these structures forming and dissolving again as stars create, live for a short time. These massive stars create and live for a short time and sweep up their environment. Then at the end, you can go back and you can query this numerical simulation to see at any point in time and any what the pressures and the temperatures are of and the densities are of these media, the different points in your simulation, and you can plot it here. And this is a pressure density diagram, so that's that phase diagram again. This black line is the thermal equilibrium curve. And these colors indicate the fraction of the mass that's in these different phases. And you can see that actually most of the mass is in these two phases, but the supernova activity has created denser, has created increased pressure phases which live for a short time. So there's a short time that you can be at a much higher pressure. This is done the distribution when you sort of fold it down onto the pressure plane. This is when you fold it down into the density plane and on the temperature plane. And you can see that in the pressure plane, most of it is in thermal equilibrium. That is again the fraction of the gas, but there are some fraction of the gas that's a higher pressure because recently a shock passed through, or a lower pressure because recently a rarefaction wave traveled through. And you have these two phases also in density. Here's the high density cloud phase. Here's the low density intercloud phase. And so the radiative heating sets the and mechanical energy input sets this pressure. And the mechanical energy input also sets the distribution of the phases of the gas over these phases. So this is then a summary, galaxy-wide over these different phases, the hot intercloud medium, so that's a collisionally ionized medium, the warm neutral medium, this interclouds, some of that is ionized, then you have the cold neutral medium, which is these clouds, then you have the molecular clouds, and you have the H2 regions. And this gives you the kind of conditions that you can find in these regions that you can look at your leisure later on. Then there is, of course, a distribution of this in the galaxy. This is as a function of galactic centric radius. So the galactic center is here. The sun is at about 8 kiloparsecs down here, and there is a molecular ring. This is the distribution of molecular hydrogen. There's a molecular ring at about 4 kiloparsecs. Atomic hydrogen is much more flatly distributed throughout the galaxy. So there's a distribution. There's also a distribution of massive stars, so of the radiation field, and of supernova activity. And for each distance from the in the galaxy, each galactocentric radius, you can do these kind of calculations, and you can calculate these thermal equilibrium curves, and you can see that depending on the distance from the center, you will have a different pressure and different conditions for your medium. So if we recap this, we have gas and thermal radiative and pressure equilibrium. We have two stable phases, the clouds and the interclouds. And these physical characteristics of these phases are controlled by the cooling curve, so by the properties of the atoms. And then we have mechanical energy input that creates these hot intercloud medium, so that the 1,000,000 degree that fills these holes and creates these cavities. And then we have molecular clouds that are dominated by gravity, which we'll come into later. And we have a summary you can find on slide 31, and it all depends on the location in the galaxy. So let's talk briefly about the energy and ionization in these diffuse clouds. Energy inputs can be coming from starlight. These clouds are diffuse, and so the light can penetrate. And this is sort of the different energy, radiative energy inputs. So here are the O and B stars, the cool stars, so that's F through M. Then there is emission from polycyclic aromatic hydrocarbons and from dust in the infrared. And then we have the cosmic microwave background at the longest wavelengths. At 13.6 eV, all the photons from the stars have been eaten away ionizing hydrogen. So there is the only emission that you have is from this hot gas, mostly in emission lines. And it's this region of the spectrum that we're really interested in, because that's the FUV, that's 6 to 13.6 eV. Those photons can ionize elements such as carbon or sulfur. Those photons can ionize molecules. Those photons can photodissociate molecules. And so those are the photons that can couple to the gas, that can heat the gas. And the heating, the coupling can go through the ionization of carbon, because carbon has a ionization potential less than hydrogen, and you can balance the photoionization of carbon with the recombination that's occurring. And when you write that out, this is the equation that you get. Is the neutral fraction, X is the ionized fraction. And you can see that the neutral fraction is for typical conditions. These are typical conditions for diffuse cloud. The neutral fraction is very small. So carbon is highly ionized in this medium, in these clouds. And heating occurs then through the photoelectric effect on large molecules, polycyclic aromatic hydrocarbon molecules, and on small dust grains. So you create a photoelectron. That photoelectron takes some of the energy away, some of the photon energy away as kinetic energy, and the kinetic energy is transferred to the rest of the gas and it's heating that gas. And this gives the photoelectric heating efficiency as measured as a function of the ionization parameter. So it's the ionization rate over the recombination rate. So when you have low electron density, everything is neutral. You have a very high photon electron efficiency because all the absorptions will lead to ionization. If you have a high UV field intensity, then everything will be ionized, and when you're ionized, the heating will drop. A large fraction of the molecules are ionized, the heating will drop. And so that gives rise to this curve. And these are some observations that have been analyzed of different regions, which show a similar trend in the behavior of the heating. This is the cosmic ray spectrum. So this is the flux of cosmic ray particles. These are the protons. These are the helium particles in carbon and iron as a function of the kinetic energy in MeVs per nucleon. And so this is 1 MeV, and this is about 1 GeV per nucleon. And you can see this is these are the observations measured at the Earth by satellites. What's the flux of these high energetic particles? And these kind of energies cannot penetrate the heliosphere. They are bent off by the magnetic field in the heliosphere, and so we cannot measure them. This is what we theoretical models predict that flux should be. And then you can, the cosmic rays are highly energetic, and so they can ionize atoms, and that ionization can lead to heating. And so this is the cosmic ray ionization rate as determined from these kind of curves. And this is determined from observation. I'll show that in a minute from H3 plus. And this is measured for dense cloud, what the cosmic ray ionization rate is. And I'll come back to that as well. So how do we measure the cosmic ray ionization rate in situ, in atomic gas? Well, we have a little bit of molecular hydrogen. Molecular hydrogen gets ionized by a cosmic ray, creates H2 plus an electron, of course. The H2 plus will react with another, is very reactive, will react with another H2 molecule and form H3 plus. And H3 plus is basically an H2 molecule with an extra proton. And when that recombines with an electron, you form H plus H2. And now we can write a balance. Everything that flows in at the top has to flow out at the bottom. So we can relate the ionization rate with the recombination rate. And then you can write this equation, which is the ionization rate, which scales with the cosmic ray flux over the density. And it scales with how many H3 plus molecules you see compared to how many H2 molecules you had. And these can be observed through H3 plus through infrared absorption lines. And we can determine the column density. The H2 column density we can determine from UV measurements. And so we can determine this side, so we get the cosmic ray ionization rate over the density. And this shows a set of measurements for this is the right side of this equation, and as a function of density for different environments, different clouds. These are all measured data, and you can see this is the cosmic ray ionization rate of 10 to the minus 16, this is 10 to the minus 17, and so depending on the environment, you have a rate that depends, ranges from 10 to the minus 17 to 10 to the minus 16 ionizations per second. Let me skip about over this and talk a little bit about the energy balance. We already talked about the photoelectric effect that's coming from these UV photons. This is when you work out what the heating rate would be from that process. And that balance is sort of the cooling rate of thermal gas. This is thermal gas that cools, and that's why it's given with a minus sign here. And other effects like the cosmic ray ionization or magnetic fields or turbulence are really very small compared to this. And this summarize this as a function of density, what these different heating processes are, and basically it's that photoelectric effect that plays the dominant role. Now I have a curve here that's labeled turbulence, that if the turbulence were sort of decaying all the time, actually turbulence is intermittent. That means that it creates shock waves that dissipate the turbulent energy. So you creates small pockets of warm gas that cools very rapidly. So you get these small temporal regions that are very warm and that cool then very rapidly. And we can see this as in the molecular composition, because some molecules need high temperatures in order to be formed. CH plus is an example, OH is another example. And so from those observations of those molecules, we know that there is warm gas, but that's not created by the photoelectric effect. That warm gas is due to the intermittent dissipation of turbulence. So summarizing it again, ionization is set by photoionization of carbon, as recombination is by anions. Temperature is set by the photoelectric effect, on pars and very small grains, and balanced by the carbon plus 158 micron cooling. And the typical conditions are of the order of 50 particles per centimeter and 80 degrees. Just as we saw before, that's what you get from a analysis of the heating and the cooling balance. Let's look at the mass balance of the interstellar medium. Then we have masses being input by low mass stars, by high mass stars, and these are just numbers. It's much more visually appreciated when we look at it this way. This is most of the mass comes from these AGB stars, so low mass stars with puny winds. But some of the mass comes from supernovae, so or high massive stars when they are luminous blue variables, Wolf-Rayet stars, or red supergiants, or B stars. But most of it actually comes from AGB stars. And that is enriched, of course, in these elements. And so because star formation depends on radius in our galaxy, the enrichment will also depend on radius in the galaxy. And so the inner galaxy is much more enriched in, say, oxygen than the outer galaxy. And the same for other elements. These are different studies done by different people. And so in a summary, really, the Milky Way is an approximate steady state where the formation of low mass stars is balanced mostly by a mass ejection from low mass stars. If most of the mass is low mass stars, in a balance, most of the mass returned has to be low mass stars as well. Circulation between the disk and the halo creates this major mixing. And stars create these elements which they then eject either in supernovas or in these AGB winds. This is in terms of the observables. Let me skip over this. And this is then a summary of what I have said now a few times already. Again, you can look at the textbook if you want more details on it. But I have also some exercises that you can go through and see whether you really appreciate and understood everything that I discussed. Let me go turn to the second part of this lecture, that's talking about molecular clouds. I have talked about, until now, I have talked about the diffuse clouds. This is a summary of the structure of a cloud as a function of column density. And so for low column densities, UV photons can penetrate, hydrogen is atomic. But if you go deeper in, then hydrogen will become molecular. And so the atomic fraction drops. The carbon is ionized in the surfaces of these clouds, but when you go deeper in, UV photons are absorbed out, and so the carbon ionization drops. Sulfur can still be ionized, but carbon goes then to neutral carbon and goes then to CO. And so we have talked until now about the diffuse atomic cloud, so these surfaces really. You have also diffuse molecular clouds where you have H2 being present, so it is molecular, but carbon is still mainly carbon plus. So you could also call this CO dark molecular gas. Then you have translucent clouds, and then you have dense molecular clouds. And so as a function of column density, you will see hydrogen going into molecular from H to H2, carbon going from carbon plus to neutral carbon to CO. The electron fraction drops from 10 to the minus 4 when carbon is ionized to 10 to the minus 5 when sulfur is ionized to 10 to the minus 7 when the ionization is carried by molecules. And the temperature for a typical cloud, a diffuse cloud, the surface is maybe 15 degrees and the interiors of a cloud are of the order of 8 degrees. So let's talk about the observed characteristics of molecular clouds. This is a crosscut of the galactic plane. So the galactic center is here. So everything, the Orion is here, Taurus is on this side, Ophiuchus is up here. And you can see that the interstellar medium is a very thin disk, and certainly molecules is really very thin, like 100 parsecs thick, while the extent of this is maybe 15 kiloparsecs one way, so 30 kiloparsecs in total. And so if you zoom in on this Orion region, then you get the Orion Cloud A and Orion Cloud B. We saw that in the pretty pictures before. This is the Ophiuchus region. And so this is old CO emission that we're seeing here. And if you zoom even further in here on this region here, then you get the integral shaped filament, and you get the 4 cores, OMC1 with the M42H2 region, OMC2, OMC3, and NGC 1977 is up here, and OMC4 is down here. And here's the Orion bar, which is this dense photodissociation region. Now we can look at clouds in the galaxy, and we can we characterize them, and we can say how many clouds are there per cubic parsec, and how much mass is in these clouds. And then you get this kind of distribution. So this is the distribution function, and this is for the optical and 21 centimeters. So these are the diffuse clouds. This is the molecular clouds. And it depends a little bit of whether you're looking at the inner galaxy or the outer galaxy, or the solar circle, how many you have. But this is the distribution function. So per unit logarithmic mass, it scales like a power law. And most of the clouds are small, you can see that, but most of the molecular mass is this kind of a exponent is in the largest clouds. You also see that it is a power law, and a power law doesn't have a characteristic cloud. The characteristics of the clouds really depend on what characteristics you're interested in. If you want to have the average size, you get a different number than when you want the average mass or when you want the average density. And so you have to put this in perspective. We are mainly interested in the giant molecular clouds because they contain most of the mass, and because they contain most of the mass, they also will be hosting most of the newly formed stars. And so there are about 5 million molecular clouds. Most of those are small, but there are about 1,500 giant molecular clouds with masses larger than 100,000 solar masses. And these are some typical sizes, 60 parsecs in size and 100 particles per cubic centimeter. Now, when we study these clouds, then we find actually that these clouds have scaling relations. So the dispersion, the velocity dispersion scales with the size to the 0.5 power. The velocity dispersion also scales with the mass to the 0.2 power, and the density scales then with 1 over the radius. And that means that the column density is constant for these clouds, typically about 160 solar masses per square parsecs, or an AV of about 8 magnitude. So UV photons cannot penetrate these clouds. Now the precise p-exponent, these coefficients depend on how you really define the cloud, what you adopt as your definition. And that's shown, that this relationship is shown here. This is the velocity dispersion as a function of radius, and you can see that there's a nice relationship. These yellow ones are defined in a different way, and that's why they're off from this relationship. But if you were to define all clouds in the same way, then these yellow ones would coincide with these other ones. And so your range of cloud properties range from about 0.1 parsecs, which is pre-stellar core, all the way up to the largest clouds, which are of the order of 100 parsecs in size. So these are your puny clouds, maybe a solar mass or so, a few solar masses. Up here, you're talking about a few million solar masses. Now, these scaling relationships are consistent with viral equilibrium. Viral equilibrium, the gravity and the kinetic energy are in balance. And the kinetic energy is actually turbulent. But so we know what the turbulent energy is, we know what the gravitational potential energy is for, and so we can just calculate this virial parameter, which is just given by a ratio of the velocity dispersion, the radius, and the mass. And when alpha ver equals 1, then you are in virial equilibrium. And so here we have again that sigma v versus, we have plotted here as a, in a slightly different way, as the radius times the surface density. And these are the observations, these colored dots. And the solid line is a virial parameter of 1, virial parameter of 3, and a virial parameter of 10. You can see that many of these clouds are close to virial equilibrium. And that's sometimes taken the other way. Sometimes you will see that this one will say, oh, I assume that the cloud's in virial equilibrium, and so from its size, I don't know its mass. That's what you do when you have not all the information. So turbulence is very important. You saw that the molecular clouds are supported against gravity by turbulence. So let's look at the turbulence in the cloud. So this is the Aquilae molecular cloud, as observed by Herschel. This was the Spire measurements at long wavelengths, so sub-millimeter wavelengths, and here, this is then translated. This is an actual observed flux. This can then be analyzed. You can get determine the column density, and this is a column density map. And so the highest column densities are this yellowish green, blue is somewhat lower column density, a few times 10 to the 21, and red is really very low column densities. You can see that there are these filamentary structures in the clouds, and the blue triangles on this are dense cores, so dense regions of gas. And then you can look at where are the stars forming. This is that same region. The filamentary structure has been enhanced using a special technique to really make it stand out. Again, the blue triangles are the dense cores, and the green triangles are the deeply embedded protostars. So class 0 protostars are deeply embedded in their cores. And you can see that they're all confined to these filaments. It's only the dense cores that can be gravitationally unstable, and that will collapse. That's what these observations tell us. And so we have this complex network of long, thin filaments that we have in this turbulent molecular clouds. These dense filaments then fragment and form these dense cores, these prestellar cores. And then gravity will select from these prestellar cores those that are the densest and that become unstable. And they become unstable when their mass exceeds this critical mass, which is the sound speed squared over the gravitational constant, which is 15 solar masses per parsec. And that corresponds to a column density of about 10 to the 22 or an AV of 10. And so this is a numerical simulation of a molecular cloud that has turbulence in it. And the turbulence, as you can see, the turbulence creates then these dense filaments. And in these, as you can see here, these dense structures. And then in these filaments, you form cores. And these cores here, you can see it start to form stars. So this is sort of the kind of life cycle of a molecular cloud, basically. Now we can then look at these simulations, and we can determine what the density distribution function is. And in a general sense, what will happen to a parcel of gas is that every now and then there will be a shock wave coming by that will give it a shock that will densify it, and sometimes a rarefaction wave will come by that will decrease the density. And these waves that propagate through are turbulent waves, shock waves, and they are Gaussian distributed. They're randomly occurring. And so the density then will be some initial density that you had times a product of, well, sometimes you get enhanced in density by a factor delta. Sometimes you get decreased in density by a factor delta I. And that leads to you can write this out as the log of the density is the log of the initial density times plus this sum of these log of these factors, these rarefaction or densification factors. And that's a Gaussian distribution that will lead to probability distribution function, but the parameter is the log of the density. It's a log normal distribution. So the log of the density is normally distributed. And the dispersion is given then by this dispersion parameter. This is S0 is the typical density that we'll have. And the numerical simulations then give you this expression for the turbulent dispersion, for the dispersion parameter in this expression, which depends on the turbulent to magnetic energy densities. It depends on the Mach number of the shocks, and a fudge factor, which these numerical simulations determine to be of the order of 0.4. And then you can look at the distribution function, the probability distribution function, as measured in clouds. It's given here in terms of the density, the column density, as a function of the AV, the location in the clouds. And this is for Lupus 5, which is quiescent cloud, no star formation at all. You can see it's beautifully represented by a log normal distribution function. This then is a Lupus 1. So it's also a molecular cloud, but this one does have star formation. You can see that the lower column, the lower regions are well represented by this log normal distribution, but there is this tail of high density cores. Those are those densest cores that gravity has taken over. Those are the densest cores that are going to form stars. And so it's this interplay of these shocks that are driven by the turbulence that creates the structure of the cloud, and that also creates these denser cores that can collapse and form stars. And then these cores can collapse, and they will form stars. You can then look at the number of objects per mass bin as a function of the mass. And this is that pre-stellar core distribution that we just looked at, that you can determine from observation. This is the stellar mass distribution. When we look at stellar masses, this is what that distribution is as a function of mass. And you can see that it's displaced from the core distribution by about a factor of 3. So star formation is efficient, but not too efficient. Only 1/3 of the mass of a core will go into forming the star. Most of it is actually lost to the interstellar medium again, or to the core molecular cloud again, either through the action of stellar winds or jets, or because the star formation stops. Let's talk about the formation and destruction of molecular clouds. Molecular clouds are important. We want to understand how they're formed and destroyed, because they can contain the star-forming regions. And there are possible formation routes. There could be a converging flow created by feedback processes. So the H2 regions and the stellar winds create these bubbles, and these bubbles become dense, and that can form molecular clouds. And an example is Lambda Ori. Then you have these super bubbles, of course. They really create these large structures. They can form large clouds, maybe 10 to the 5th solar masses. An example is W3, W4, DR21, and Cygnus X. Then you have coagulation in spiral arms. When the gas goes through a spiral arm in the galaxy, it will be compressed, and clouds can collide and coagulate. And an example is W43. And then you can have large-scale instabilities in the disk of the galaxy. Destruction routes are, well, you can have feedback from protostellar jets. So a local example is the Serpens cloud. You can have feedback from ionization, and an example is Sigma Ori and the L1630 cloud. Stellar winds. You can have the Veil Nebula and the Theta 1 Ori, and then you can have supernovas, which can create these super bubbles, but which can shred clouds as well. So let's go through some of these examples. It's always good to have some pretty pictures. Astronomy is famous for its pictures. And so this is the Lambda Ori. We have seen that before. That was the head of the Orion constellation. So you can see that this is the shell that's being created by the wind from the stars here, and that's swept up into this and forming these denser structures, which are molecular clouds. So this is of the order of a few parsecs in size. Here we have the W3, W4 region, where W4 has a rich cluster, IC 1805, which has many, many, many O stars. It's already 5 million years old, so many of those O stars have exploded as supernovas, created this big bubble here, and that bubble has swept up gas into its surroundings. In fact, here it formed a dense secondary molecular cloud, which is the W3 region, which is now starting to form stars as well. So that's two ways how the feedback activity can create molecular clouds. Here we have W43 schematic. So the clouds are entering the spiral arm. They get densified, the stars form in it. You get the star formation take place, the shells that are formed. You get then the supernovas that explode, that create these big chimneys. And you get the initial formation of the cloud is because you have small clouds that come together and coagulate into this molecular arm, the spiral arm, and form a high dense gas concentration, which then becomes gravitationally unstable. Here we're talking about the destruction of the cloud. So this is the Orion Veil that we have seen before. So here's the trapezium stars, which are creating this large bubble, and eventually that bubble will pierce and will break open. And when it breaks open, it may be another 100,000 years or so, this hot gas will dissipate. This material will flow away. This is about 1,000 solar masses of material that will flow away and float away into the surrounding medium. So this is a massive star that's creating all the havoc and destroying the molecular cloud core from in which it was formed. Here we have the serpent cloud. So these are low mass stars, and these low mass stars have jets indicated here by these blue and red lobes. So there's a star here that has a jet, and the jet sweeps up the material and it creates these lobes, and that destroys the molecular cloud as well. This is a slightly different destruction of a molecular cloud. What's happening here, this is the Orion B molecular cloud. And you can see that stars are being formed in it. This is a massive star that will affect the molecular cloud. But actually the main destruction agent here is this star Sigma Ori. Sigma Ori actually was formed in Orion A, which is over here in the sky. It has traveled for about a couple million years, 2 million years. Finds itself now close to this molecular cloud B that's here. The ionization from this ionizing photons from this star ionize the surface of this cloud, and that creates this flow from the ionized gas into the medium. Because this is very hot and very dense gas that then can expand basically in an empty vacuum. And so this is a destruction, a chance destruction, because a massive star meets a molecular cloud and decides to destroy it. And of course, you recognize this. This is the horse head, and so this is L1630 in the horse head. And this is one of the belt stars. So the Orion belt is up here. So what have we learned? Well, we have learned that turbulence is the key to the structure of molecular clouds. It's also the key to star formation because it creates these dense cores. It typically is created, it's dissipated turbulence in a sound crossing time, which is of the order of free fall time, and it's much shorter than the cloud lifetime. And so we have to replenish this turbulence by the protostellar wind activity, the jets from the serpents in the serpent's cloud, for example. We can replenish it by mass accretion from the diffuse clouds. If you accrete mass onto a molecular cloud, then you add the turbulent energy, and you can have cloud-cloud collisions, which also drives turbulence into the medium. Let's talk about the physical characteristics. So the heating, the surfaces are heated by FUV photons, just like the diffuse clouds, just like photodissociation regions. But the molecular cloud, the proper molecular cloud, is mainly heated by cosmic rays, because UV photons are absorbed in the surface layers, while cosmic rays are so energetic that they can penetrate much deeper into the cloud. Now, the densest cores are heated by ambipolar diffusion, where the magnetic field sort of drifts out, and as it drifts out, it takes the ions along, and the ions collide with the neutrals, and that drift between ions and neutrals creates some friction, and that friction heats the cloud. Then inside, when the dense core starts collapsing, of course, you're densifying it, and when you densify it, heat is released. It's adiabatic compression, basically. And around protostars, you can also have collisions between the gas and the dust, where the dust is warmed by the photons from the protostar. And then you have turbulence, which again will be dissipated intermittently. We have seen that already, and creates these small regions, small pockets of warm gas. The cooling is dominated by molecular cooling now. There are no atoms around, and the cooling then this is the cooling rate as a function of density, and at low densities is dominated by CO. At higher density, other species come in and start to contribute to the cooling as well. At high densities, your molecules can actually be depleted into ices, and then it's really gas-grain collisions that control the energy balance. And then we can use the molecules to probe the physical characteristics of a molecular cloud, and to understand that, we have to look at a simplified molecule, a molecule with just two levels, a lower level L and an upper level U, and those levels are connected by collisions. So collisions take you up, collisions can also take you down, but you can also be taken down by radiative transition, indicated here by the Einstein A coefficient. And then you can write down a balance equation where the collisions upwards are balanced by collisions down and by radiative transitions down. That's this equation here. And you can rearrange that, and when you do that, you get this relationship that the level populations, the density in the upper level over density in the lower level, depends on statistical weights, of course, but then there is this Boltzmann factor, but it's mediated by something that's the critical density over N naught. And basically what it says is that when you're at high densities, collisions dominate. And collisions up and collisions down dominate. That means that you're in thermodynamic equilibrium. You're being controlled by the thermal temperature of the gas. And you get a distribution, which is basically the Boltzmann distribution. This term is not important anymore. At low densities, on the other hand, it's collisions that take you up, but actually you fall down radiatively before you can be collisionally de-excited. So collisions taking you up, radiation that takes you down, and that means that the density is low compared to the critical density. That means that this term dominates. And in that case, this is the expression. And so it's you're falling out of thermodynamic equilibrium. Your level populations is much less than what you expect for thermodynamic equilibrium, and it depends on the density, as you can see. And that makes the level population sort of a density measurement. You can measure the populations of the levels of a molecule. Then you're basically measuring the density if you are in this limit, not if you're in this limit. And so you can use that to you can use molecular transitions to determine the density and the temperature of the gas. And this is then the column density as a function of the energy of the level. This is for methanol. And so you're probing a lot of different energy levels, and you can see that this is the distribution. And if you had a Boltzmann distribution, it would be a straight line. So here you have this is for 13 methanol, and here you do have a Boltzmann distribution and a straight line, which is characterized by a temperature of about 27 degrees and a column density of 7 times 10 to the 15s in this. And so you can measure the temperature, the excitation temperature this way. This one you get deviations because you are not in thermodynamic equilibrium, because you have a density which is less than the critical density. And you can work that out, and it depends then on how optically thick your transition is. This is the temperature compared to the excitation temperature, so of the gas, and as a function of the density over the critical density. If you're in thermodynamic equilibrium, the two are the same, but if you are at low densities, then you'll fall out of thermodynamic equilibrium, and then your excitation temperature of your level is much less than the kinetic temperature of the gas. And how fast you will drop out of equilibrium will depend on what this excitation temperature is compared to the energy separation of the levels. You can work it out, and I did this here. It will depend on whether your photons can escape or not. If your photons cannot escape, if they are trapped locally because you're optically thick, then basically what happens, you have a transition down at one point, but the molecule nearby will absorb that photon and will be excited up. And so you haven't really lost that excitation. You only lose the excitation if the collision takes you down or if the photon escapes. And that depends on the optical depths. And that can be very important for, say, CO. The CO1 to 0, this is the optical depth as a function of various parameters, and I filled in some typical values. The line width, if the line is broader, then it's easier to escape. If the column density is larger, then it's less easy to escape. You get a higher optical depth. This is the typical values, and you see for typical values, the optical depth is of the order of 35. Which basically means that it's very likely that you are absorbed again before you escape. In fact, it's a random walk, and you have to have about 1,000, close to 1,000 of these interactions, absorption and re-emissions, before you make it out to the edge of the cloud and you can escape. So this beta factor is of the order of 5 times 10 to the minus 3, and that means that this critical density is of the order of 5 particles per cubic centimeter. So CO is typically always in thermodynamic equilibrium if it's optically thick. CO1 to 0. That's for the main isotope. The 13CO is down in abundance by a factor of 65, so it typically is not optically thick. Its photons can escape, and its critical density is more of the order of 1,000 particles per cubic centimeter. So that's talking about the density, how you can determine density. Let's talk about temperature. Lines can also be thermostats. This is ammonia. And ammonia has not just a principal quantum number J, but also a K. That's the projection of the quantum number on the rotation axis. And these different Ks, there's no transitions between the different Ks. You can only change delta J plus minus 1, and delta K is plus or minus 1 or 0. And so you cannot make a transition from this ladder to this ladder. You are stuck in these different ladders. And that means that these lower levels, everything in these in this K equals 0 will decay down to this ground state. Everything in this one will decay down to this one, and everything in this ladder will decay down to this one. But these ladders do not radiatively couple. They do collisionally couple. But because they cannot radiatively couple, they're always in thermodynamic equilibrium. So the level populations are always regulated by the temperature. And the temperature energy difference is of the order of 15-20 degrees. And so that's a very interesting temperature energy difference, because temperatures are of the order of 10 degrees in molecular clouds. And so this is a very good thermostat. Ammonia is a very good thermostat to measure the temperature of the gas. And that's done here. This is the I forgot, it's the serpent cloud, I believe. And this is the temperature ranging from about 10 to about 20 degrees in the yellow. This is the intensity on that same scale. And you can see that you can actually measure the temperature fairly accurately in these regions because you have this ammonia. Ammonia is you have only enough column density when you're in the denser cores. So you can see here the denser cores that are measured very well and are slightly more hotter than the environment, basically because stars have formed in them. So you can also measure the temperature because you can measure the temperature of the dust, and the dust and the gas are thermally coupled through collisions, particularly at higher densities. And the dust temperature you can measure through the spectral energy distribution of the emission. And so these are the B68 cloud measured at different wavelengths. And so for each point, you can determine spectral energy distribution. You can fit that. You can get the temperature and the column density, and you can plot this temperature then as a function of radius. And so the surface of the cloud is here. It's about 17 degrees. But as you go deeper in, it quickly cools down to about 8-9 degrees. And so the gas temperature will be very closely coupled to this. Then you can get the column densities. You can determine the column densities by assuming that from the 13CO measurements, assuming it's optically thin. So then it's a measure of the column density, but you need to know the temperature because you need to know what the excitation is, and you determine the temperature from 12CO. And once you have the column density, then you can assume a scale size. And if you have a scale size and a column density, you can determine the density just by dividing the two. There are some issues with this because you can be subthermally excited. 13CO is typically subthermally excited, but 12CO may be thermalized. So the temperatures, the excitation temperature of 13CO and 12CO are not the same. 13CO may also be optically thick certainly when you go to a denser core, and then you have to use an even rarer isotope, 12C18O, which is down in abundance by a factor 500 from the normal isotope. Yeah, but that's of course more difficult to observe. Also, of course, if you want to get a density, you have to assume a abundance of the CO and an isotope abundance ratio, and you have to know those, and you have to basically calibrate this somehow. And you have to remember that you may have an isotope abundance gradient in the galaxy. And then in the deepest interiors of the core, the CO may have frozen out, and so you may miss that. And you may not have good measurement density. But you can do this, and also through dust extinction. This is again B68. This is in the visual wavelengths. You can see that the cloud is opaque, but if you look in near infrared, you can start to pick up many stars, and you can determine the extinction of those stars. So this cloud has some 3,000 stars, of which maybe 1,000 are heavily extincted, so you can use that. You can measure the extinction, so you measure the color difference, and the color difference is translated into a visual extinction through an extinction law, and then you have to assume a dust to gas ratio in order to get a column density of hydrogen. And then when you smooth it, you get this resulting density distribution for this cloud that looks like this. This is the column density as a function of radius. So here's the surface, here's the densest interior. And what is plotted, this curve that's plotted here is the expected density distribution for isothermal core that's in virial equilibrium, which is fitting pretty well. You can, I think you can also determine the column density from the dust emission. We did it from dust extinction before. Here in the previous slide, here is the same cloud, B68, measured at different infrared wavelengths. So the emission, we have seen this cloud, this set of images before. We can make a spectral energy distribution at every point. We can fit that. We get the temperature. That's how we determine the temperature of the dust. But you also get the column density, you get the optical depths. that optical depth you can then translate into a column density of hydrogen if you have a model for the dust to gas ratio. And this was done by the Planck collaboration at 353 gigahertz, and this calibration. And this gives you the temperature. We saw that already. This is temperature distribution. This is the column density distribution that goes with it. And again, it goes very well. It's very well fitted by this isothermal sphere distribution. And then if you adopt the scale size, you know, this, for example, then you say, oh, I can translate this into a density. Another way you can do it is by looking at the excitation of your molecules. I said before, if you have the level population in the upper level compared to a lower level, that's density and temperature sensitive. And if you take a right set of molecular transitions, then you can get something that measures the density and something that measures the temperature. And then you can take those data to determine the density and temperature in a specific point. And that's illustrated here for 3 levels of formaldehyde. And these two are sensitive to the temperature. You can see these curves here are indicating constant levels of constant ratios of those levels. Oh, excuse me, of those lines. And the colors are also giving that line ratio, but then in a colorful way. These dots are all different observations of a particular cloud. And you can see what those where you are in sort of a temperature phase. Here we have the other set of lines, the other ratio, and this one is more sensitive to the density. This is density, this is the temperature, and you can see that these lines are almost vertical in the region where the most of the data points are. Most of the data points are in between these two ratios. And then you can combine these two and you can get density and temperatures where this line, for example, intersects with the line that corresponds to its to the ratio observed for that point in this diagram. And so you can do this. Methanol, formaldehyde is often used, but others are possible as well. Denser regions often use methanol or methylcyanide. But it's basically the same as I explained a few slides ago. It's basically using the excitation between 2 levels. You measure the population at one level and the population below it, in the level below, and then you compare those two, and that's sensitive to density and temperature. And then I said you can pick, you have to pick the right density and temperature tracers because they have sort of to match the conditions in the cloud that you're interested in. And there are a variety of species that you can use for this. And that's sort of illustrated here. Here's the density along this axis, the kinetic temperature along this axis. And these blocks indicate where a molecule or set of lines is particularly useful as a density temperature measurement. Because, of course, the level separation has to match the temperature. If your level separation is much larger than the temperature, then the upper level will never be excited. If it is much less, then it will not be sensitive to the temperature. The same that the critical density, the density has to be in between the critical density of the lower level and the upper level, so that one is in thermodynamic equilibrium, the other one is not. And then you can take CO, low JCO are sensitive to low densities. Maybe 100 particles per cubic centimeter, temperatures below 30 degrees. The higher JCO lines have a larger Einstein A and therefore may have a higher critical density, so you need somewhat denser gas. They trace somewhat denser gas, and of course also somewhat warmer gas because they're higher up on the ladder, and so you need more energy to excite them. And molecular hydrogen has only forbidden lines. Forbidden lines have very low transition probabilities, and that means that they're always in thermodynamic equilibrium, and so they are very good low density tracers. But molecular hydrogen has large energy separations, and the lowest energy is actually at 28 microns. So it's about 500 degrees, and so you need really very warm gas in order to excite those. Then you have your light hydrides, things like water or OH or ammonia. A light hydride means that it has a large moment of inertia. A large moment of inertia means that they have large energy separations between the levels. And if you have large energy separations, then the Einstein A is very high, and that means that you need a high density in order to excite them. And so you can see that the different molecules trace different regions. This sort of summarizes that in a visual way. And you have to select the right tracer to determine the conditions in the region that you're interested in. And you should actually think about this the other way around, because you always have a distribution of densities and temperatures along your sight line, and the molecule or the transition that you select will determine which gas you're actually measuring. If you may take the low JCO lines, you will always measure low density, low temperature gas. But if you measure the light hydrides, you will always measure much higher density gas that's along your line of sight, because the low density gas will not be seen. Let me talk a little bit about the ionization. We have seen this already in diffuse clouds. Cosmic ray ionization determines the ionization in clouds. And so you start off with H2, that is ionized, you form H2 plus an electron. The H2 plus reacts with another H2 to form H3 plus, which is an H2 molecule plus a proton. That could recombine with an electron, but actually what it probably will do is transfer that proton to another molecule that likes protons more, that has a higher proton affinity. And CO is such a molecule. And CO is very abundant, so basically what you form is HCO plus. And the HCO plus can recombine with electron, forming H and CO. And so this is the flow down, and you can again write an equation that relates the how much ionization flows in on this end and how much recombination flows out on this end. But the H3 plus can also transfer that proton to HD. HD likes protons a little bit more than H2 because of small difference in 0-point energy. And the HD to D plus will also transfer its proton or its deuteron to CO and form DCO plus. And DCO plus can recombine with electron and form CO plus D. And you can write down these two equations, and then you can, we cannot measure H3 plus in molecular clouds because we don't have bright sources in the infrared that we can study. And so we need another tracer, or a molecular tracer to get the abundance ratios and to get the ionization. And we do that by using H to D plus or DCO plus and HCO plus. And so when you plot the DCO plus over HCO plus ratio as a function of the HCO plus over CO ratio, then you get these curves, and there's two sets of curves on it. I don't want to go into the differences. It's not so important here. What is important is that we can determine these ratios from observations, and these curves depend on the ionization rate over the density, just like the H3 plus ones that I showed before in the diffuse clouds. And so this ratio is of the order, is 3 times 10 to the minus 21 in this ratio, and with a density of 10 to the 4th, that means that you have an ionization rate of 3 times 10 to the minus 17. So we can use molecules as a probe of the universe. We can, we have talked about the role of molecules in the evolution of the universe. And of course, molecules are also important in the origin of life. We have talked about molecular clouds. We have talked about the physical characteristics of an ensemble of molecular clouds. And we have talked about how they link to the ecology of the interstellar medium, basically because they form the stars. We have talked about the evolution of molecular clouds and the importance of feedback processes that destroy the molecular clouds, but that also form molecular clouds and that enable the star formation. Turbulence was very important for the density structure, but the clouds are mainly heated by cosmic rays and cooled by molecular line emission. Dust-gas interaction can be very important in molecular clouds through the thermal coupling, but also because gas can accrete on the dust and form an icy mantle, and that depletes the molecular abundances and therefore affects the cooling. We have talked about how we can use molecules to determine the physical conditions inside molecular clouds. And then other lectures will talk about the chemical composition of molecular clouds and what processes, chemical processes, are important for molecular clouds. So let me point you back to some of the resources that are available, the two textbooks. Then there is a spectroscopy database for molecular transitions, two actually. This is the one in Cologne, and this is the one at JPL. Then there is a molecular excitation database that is in Paris that gives you collisional excitation rates and the properties of molecular levels. And then there is a molecular emission tool, the RADEX tool, that's really very useful if you want to calculate what the emission is that you expect from a column density of a molecule at a given temperature and a given density. Then this model can calculate for you what the expected intensity is. And with that, I have reached the end of the lectures, and I can open the lecture to questions that you might have.
Yeah, thank you very much, Alexander, for very interesting and informative lecture. So please write your questions in the chat, and I think we have already one question from the beginning. So the question was like this: if the young supernova nebula still contains a significant amount of hydrogen, can a new star form inside this young nebula? Or it was also more precisely specified, could, for example, shock waves create some higher density somewhere in this area and lead to the formation of the new star? Yeah.
That's a very interesting question. Think about a massive star, let's say 40 solar masses, 30, 40 solar masses, goes supernova. It ejects all of that material in random directions, 4 pi, and while it expands, it really rapidly dilutes. And eventually, of course, it will sweep up mass in its surroundings, will slow down, and we'll get the shock wave that we talked about, that is mentioned in this question. But the amount of mass that's contained within any of the clumps that you form is very, very small. There really isn't enough mass, and the gas is very warm, and so gravity never will dominate in that environment. It can never directly lead to the formation of new stars. But eventually, of course, the supernova will expand and sweep up enough material from its surroundings that it will form regions that are massive and dense enough to collapse. I remember that you needed a column density of 10 to the 22 for a cloud to become gravitationally unstable if it were 10 degrees. And if you have a higher temperature, it will be much more than that.
Okay, thank you. So the next question: is it valid, for example, to construct a rotational diagram of CH3OH that includes transition of E and A isomers? Or should only one configuration be taken into account for that molecule?
Yeah, I think so. I'm not an expert in this, but I think so, because I think these are basically different in a way. They are different versions of the same molecule that don't interact very easily.
Okay, thank you. So the next question, could you talk about the pH molecules in ISM? What do you know about them? And what are the open questions related to pH? Just.
Oh, that is a question that could lead to a whole different lecture. And if you're not careful, I could ride my hobby horse through this audience. There is a lot known about pHs, and it's discussed in my book, in the molecular astrophysics book, in two separate chapters. So there is a lot known. In short, we're talking about polycyclic aromatic hydrocarbon molecules. So they may consist of hexagons fused together like chicken wire and decorated with hydrogen at the edges. They contain about 10% of the elemental carbon in the interstellar medium. They're very abundant. We're talking about abundancy of 10 to the minus 7. So that's really a very high abundance for such complex molecules. And they regulate the photoelectric effect on that heats the gas. They regulate the degree of ionization in molecular clouds, and they of course dominate the mid-infrared emission of typically of all interstellar mediums of galaxies as a whole. And that's really very short. I mean, I could go on, but let me not do that.
Okay, thank you very much. And the next question, elements higher than iron are only formed during star death. Is it true?
I'm sorry, during what?
Star death. The death of star.
Elements higher than iron are formed when you have an excess of neutrons. You need an excess of neutrons, huh? Because iron is the most stable element. If you keep adding neutrons, you don't add as much energy per nucleon, and so you can't burn that way. You can't form them by nuclear burning inside dense stars. So you have to form them because you have an excess of neutron which you just dump into these into pre-existing elements. And so they're formed in neutron-rich environments. So there could be two merging neutron stars. And it could be inside an AGB star where you have excess neutrons available from carbon-13 decay. And you can also form them in supernova type 2 explosions.
Okay, thank you. So the next question, where did the early cosmic rays come from?
I didn't touch about the origin of cosmic rays. And so where do cosmic rays come from is a very good question. We think they come from acceleration of atoms across a shock front, across the magnetic field associated with the shock front. The magnetic field basically acts as a mirror. So when you have an ion will gyrate around the magnetic field, and every time it gets out of the shock front, it will be accelerated back into it and then reflected back. And if you have the right energy to mass ratio, then you will be accelerated up, depending on the magnetic field, of course, the magnetic field strength, and you can reach giga electron volts easily. And so those cosmic rays, the low energy cosmic rays, say between 1 and 100 MeV per nucleon, those are the ones that we are interested in when you talk about molecular clouds. Those are created by supernova explosions, where you have a shock between 100 and 1,000 kilometers per second, and you have gas flowing across it and being accelerated.
Okay, thank you. And the next question, how can we use the knowledge of cosmic matter cycles and environmental conditions in space to inform and guide the search for life on other planets and stellar systems? So yeah, good question.
That's more than a life's long work. And basically, you do what an astronomer does. You can't go back in history, but you can look at systems that are similar, systems that you think are similar to say the Earth or the solar system, but that are earlier in their evolution. Then you can compare these systems at different evolutionary stages, and from that get a picture together on what the Earth experienced over its lifetime. And so by going back to these planet-forming disks deeply embedded in the molecular clouds, you can sort of see the equivalent of the solar nebula when it was just being formed. And so by determining the molecular content and determining of those regions, by determining the processes that are important in these regions, you can learn about what was important for the early stages of the Earth's formation and what was available in terms of the molecular inventory, organics, volatiles, water, what was available to the Earth early on.
Okay, thank you. The next question, what percentage of organic reactions are dependent on light and photonic reactions in the SM?
All molecules in diffuse clouds, you find some molecules, not very high abundances, but you find some molecules. All those molecules are being destroyed by photons. They're really basically being controlled by a molecule is formed by a collision and then immediately destroyed by a photon. That keeps because photons are so important, that keeps them down. In a dense cloud, molecules are not very abundant. Excuse me, photons are not very abundant, and therefore photon reactions are much less important. And in that case, all reactions are driven by cosmic rays ionizing hydrogen and that ionization being carried on. Or they are formed by reactions on grain surfaces. But the UV plays much less of a role. And so I cannot put a number on how much it is, but it's much less.
Okay, thank you. So the next question, how much of this lecture applies to elliptical galaxies? Are there ISM similarities to spiral galaxies? Okay.
Elliptical galaxies are galaxies that are sort of dead. That in the sense of evolution. They're not really evolving very much anymore. And that's because they don't have an interstellar medium. And that's because they only have old stars. And the old stars evolve very slowly. And they lost all their gas one way or another in the past. And the stars die the low mass stars die very slowly. They eject material very slowly in the interstellar medium. And so if you were to wait long enough, you would get some interstellar medium back. And you would have these same kind of processes playing a role. But generally, they don't play much of a role because you don't have an interstellar medium. There are a few examples where that is not the case, where there is some interstellar medium left or replenished from these stars. And there you can see the activity taking up again.
Thank you. The next question, do you think carbon particles emission after the excitation can lead to another reaction for their near active molecules?
Oh, what an interesting question. Can you use particles in general? Can you use particles as catalysts? I think that's what this question is asking. And can you have interaction between the gas coming onto the grain, interacting with the grain, and being dissolved in a different form? And yes, they can. Generally, it's a passive interaction, The surface only acts as a meeting place, so where the species come and they meet and they react. But there are cases where, say, an iron surface and a warm gas, where you could have CO converting CO into methane, for example.
Okay, thank you. The next question. To which extent are chemical models exhaustive in explaining the spectroscopic observation of molecular clouds?
Now you come to the heart of where every astronomer has to fall on his knees and beg forgiveness. Because we call a model a good model if it explains observations to within a factor of 10. And we call it an excellent model if it explains observations to within a factor of 2. And that's, you have to realize that unlike a laboratory, we do not have control over the density or the temperature or the pressure in our medium. We have to estimate this from the kind of observations that I outlined. There's always an uncertainty with this. And that uncertainty also translates into our models. We don't really know what the model is. And then we can have a line of sight with different densities and different temperatures along the line of sight. And so you have to, and then the last thing that I should mention is that many of the reactions that we are interested in have not been measured in the lab. The rates have been determined by educated guesses. And these have been guessed by some of the cleverest people, the cleverest astrochemists in the room, but even they can make mistakes. And it sometimes happens. And when we discovered that the reaction is not as fast as we thought, or much faster than we thought, then we have to revisit the models. And we can analyze this. People have done that. They have taken a model and then just varied the different weights by a factor of 50% or so, or factor of 2, and see what the influence is on the abundances. And that tells you sort of how well you can trust it. And it also tells you that, yes, a factor of 2 agreement is pretty good. You can be happy with that.
Okay, thank you. There is one also question to clarify your previous answer regarding the particle and the reaction on their surfaces. Can we trace and characterize their transition states?
If you want to do that, you have to do quantum chemistry. And can quantum chemistry do this? Yes, it can mimic a surface. It can mimic, it can model it. There are techniques to use density functional theory, for example, with suitable basis sets and functionals. And you can model something that's maybe a few hundred atoms. And you can have the interaction of that with a small par molecule, say naphthalene, and get results that are trustable. You can compare the characteristics with studies that you do in the lab. So yes, in principle you can, but there are limitations.
Okay, thank you. So the next question, is it true that the density of molecules is very low in the ISM? If so, would collision still be a major process? Can one still use molecules in probing the physical parameters?
No, that's a very good question. Densities are very low, but timescales are very long. And the timescales to compare with are the radiated the excitation rate, for example. If a rotational transition takes maybe 1,000 seconds to relax, and so if you have a collision in that time scale, then it is the collision is important. If you don't have a collision in that time scale, it's not important. That was the discussion that I had on terms of the critical density. So if your density is close to the close or above the critical density, you're in thermodynamic equilibrium, and the excitation is described by the kinetic temperature of the gas. If the density is less than that, then you have an excitation temperature. You're not in thermodynamic equilibrium, and that has some influence not only on the excitation but also on the reaction rates. Reaction rates are always determined, measured in the lab, typically in thermodynamic equilibrium, so they're not state selective. But if your upper states are not populated, then the molecules may not have enough energy to drive a reaction. And so that may be an issue that you should keep in mind and that you should evaluate.
Thank you. So the next question. I heard about black hole supernova. If it is true, is there any organic or heavy element contained molecules in its explosion? Okay.
Yes, the answer is yes. So supernovas, when they explode, they are of course very hot, but as they expand, they cool down due to adiabatic expansion. And if the environment is if there is a clump in this supernova explosion, then you can have molecules. And so I showed the example of gas A. And gas A has CO molecules. We can observe their transitions. Another example is the Crab Nebula. And in the Crab Nebula, we have seen the molecular hydrogen. And so you can have molecules in this. And again, you have to remember, the gas A supernova is, 500 years old. So there is a lot of time in which you can have collisions and can form molecules. And if you're shielded in a dense clump, a little bit denser also, then you can have molecules present.
Okay, thank you. So the next question, what would be the chemical reaction that you would like to know the precise rate the most?
One, I get to pick my most favorite chemical reaction. I'm mostly interested in the photochemical interaction with polycyclic aromatic hydrocarbons. So what is the reaction that, and there's not one reaction, but it's a set of reaction that takes a large power molecule and breaks it down to its components. And it may also drive isomerization and the conversion of these power molecules, which are planar molecules, into three-dimensional structures like the fullerene, the buckyball, the soccer ball molecule, C60.
Okay, thank you. So let me also ask one question. So you talk a lot of turbulence in molecular clouds. How much those turbulence is taken into account in the chemical models? And can this turbulence actually change a lot the abundance of chemical elements?
Yes, because the turbulence because you have motion between the atoms, and in general, on the molecular scale, the flow will be laminar, and so there is no difference. That you don't see the turbulence velocities. The velocity difference is really between eddies, between different scales in the turbulence. But you can have situations where you have your ions behaving differently from your neutrals. And in that case, you can have velocities, drift velocities, which are higher than the normal thermal velocities of your species. And that could drive chemical reactions. That has not been studied very much. Most of the turbulence studies have focused on, hey, what happens when you have turbulence? You have a shock that you create. You get warm gas of maybe 2000 degrees. What is the kind of chemistry that you drive in that kind of gas? But it's an interesting, very interesting question.
Okay, thank you. So we have a next question here. For a reaction rate constant, of what order can be termed significant or insignificant in terms of chemistry in the ISM? What is the role of the density of the chemical species in making this judgment?
Good question. If you think about molecular hydrogen is very abundant, and so it doesn't need a very high rate in order to have the reaction be very relevant. But if you talk about a reaction involving, say, HCO plus, which has an abundance of 10 to the minus 7, then it, of course, does become important. Now, for HCO plus reaction rate, it will react at a rate of 10 to the minus 9 parts per cubic centimeter per second. For molecular hydrogen to be important, its reaction rate could be down by many orders of magnitude. 10 to the minus 11 could still be very important or very relevant. While a reaction of 10 to the minus 11 for an ion would not be as relevant, because it would have other reactions that could occur at a rate of 10 to the minus 9. So the question is very wide in assessing that it depends on the collision partners. And so there are a set of rules that you can write down. A set of the rules of the game when you put down, when you try to write down a chemical network that's relevant for molecular clouds, a set of rules. And I write those down in my chapter in molecular astrophysics. I think it's chapter 10. Or chapter 4 maybe, where it really gives these rules of engagement that help you decide when is my reaction network big enough, and which reaction should I really worry about, and which reaction should I really include, which reaction should I study in the lab, because they might be important or not.
Okay, thank you. So the next question here. But doesn't black hole huge gravity cause the collapsing and destruction of atoms and molecules into primary constituent particles? Do you think is there those elements I mentioned in explosion still? Okay.
Yeah, let me take a step back and talk about a supernova remnant. So you have a massive star, and it goes through various burning stages. First burns hydrogen into helium, then helium into carbon, and carbon into oxygen, and oxygen, neon, all the way up until you reach iron. And when you reach iron, then that's the per nucleon, you still release energy when you put and fuse atoms together. But beyond iron, you don't release any energy when you fuse atoms. In fact, you lose energy. And so once you reach iron, there's nothing that can heat the interior of the star. And at that point, gravity will take over, because there's no thermal pressure that can keep up the weight of the surrounding medium. And so what you get is that the whole star will collapse. And the inside will collapse faster, will form either a neutron star or a black hole. The outer layers will fall on that and will fall basically on a brick wall and will bounce out. And that bouncing out of the outer layers is what leads to the supernova remnants. The inner layers that form the neutron star or that form the black hole are trapped. You will not get the neutron star is sitting there, and the black hole, you won't get those atoms back. And
Okay,
so the supernova remnants that we see are the bounce back layers that saw the wall of the neutron star or the black hole.
Thank you. I have my last question about iron. So you showed this supernova remnant slide for the distribution of different elements there. So I was surprised because iron actually was not present in the center of this remnant area, while silicon and other elements were there. So where is iron in the middle? Why is it not there?
Probably because it was ejected faster. So in the form of bullets, and so made it out faster than the rest. So
iron is swept out much faster than other elements.
Yeah, and you have to remember, of course, also that you're looking at a 2D projection of the shell that was formed. But I think that's what it is. So that it's in pockets, and those pockets may move at different velocities. You can actually also see that there are some of those pockets that have escaped the rest of the supernova remnant. They're outside of that supernova remnant.
Okay, thank you. So our time is running out, and also I don't see other questions here in the chat.
Well, let me emphasize that if you have any other questions, you can always email me. I don't have it on here, but it's on the starting slide. You can email me and ask the question. I'll be happy to address any questions that you might have.
Oh, no, something new is coming. So, no, it's just thank you. Yes, we should now all thank you, our lecturer again, Xander. Thank you very much for a very nice, beautiful lecture. Very clear. Yeah, thank you.
Bye.
Yeah, with this, let's finish our today's lecture. Bye-bye.